In this lecture, we're going to prove that if we have a linear program with a totally unimodular constraint matrix, then the optimal solution is going to be integral. The linear program we're going to look at is going to have this matrix notation form. The matrix A, defining the constraints, is going to be a totally unimodular matrix, and the vector B is going to be an integer vector. The optimal solution we'll call x star. What we're going to prove is that x star is going to be an integer solution underneath these conditions. And actually, we're going to prove something stronger. We're going to show that any basic feasible solution to this linear program is going to have integer solutions. Because we were able to model flows as a linear program with a totally unimodular constraint matrix, this is going to imply that flows also have integer solutions. A key concept we're going to need for this proof is the concept of a basic feasible solution. To understand this idea, we've rewritten our linear program. Instead of in matrix notation, now we've expanded all of the entries of the matrix. Our constraints now are written by the entries of A, and our vector B is now expanded out into the particular entries of it. A basis, B, is a set of indices, and it's the set of indices referring to the variables in our linear program. Associated with any basis is going to be a solution. We're going to focus on bases that result in feasible solutions. We're going to call this feasible solution XB. A basis has a few properties. First, for any index that's in the basis, that implies that our basic solution associated with this basis has a positive value. For any index not in the basis, that means that our basic solution has a value 0 at this index. Since we're assuming our basic solution is feasible, the constraints are satisfied for our solution XB. And also, every basis corresponds to a set of tight constraints. We're going to call these tight constraints C, that is, C indexes all the constraints that are going to be tight for this particular basis. There's a one-to-one mapping between bases and tight constraints. To simplify our life, we're making a few assumptions about our basic feasible solution. First, XB is feasible. Second, XB is going to be non-degenerate. By non-degeneracy, we mean that whenever we have an index inside of the basis, it's going to have a strictly positive value. This is going to be important in our proof. To get a little bit of a better understanding of what a basic feasible solution is, we can look at geometry. Here we're drawing the polyhedron for the constraints of a linear program. The basic feasible solutions correspond to all of the corner points of this polyhedron. Every corner point corresponds to a particular basis, and every basis correspondingly maps to a particular corner point of our polyhedron. An interesting property of a basic feasible solution is that at any one of these corner points, we're going to have that the cardinality of our basis, that is the number of indices that are positive, is going to be equal to the number of constraints that are tight. We're not going to prove this, but it's intuitive from a geometric perspective. If we have a particular point, it has to be defined by a set of constraints that's equal to the dimension of the space that it resides in. We're going to use this in our proof. Our proof is going to start by fixing a particular basis B and looking at the constraint matrix associated with our linear program. Here we have a totally unimodular matrix A, our basic feasible solution XB, and our right-hand side vector B. We've written our basic feasible solution over here in a particular way. This is so that we can see which columns of our matrix A correspond to which values of our basic feasible solution B. Our strategy is going to be to take our constraint matrix A and our vector B and get rid of all of the rows of the matrix that are no longer useful and get rid of all the columns of the matrix that are no longer useful. We'll start by removing columns of our matrix. Any column of the matrix associated with a 0 in our basic feasible solution won't be considered in any of our constraints. That's because it's multiplied by a 0. So we strike out every column associated with a 0 in our basic feasible solution. We also strike out the corresponding value inside of our basic feasible solution. We're also only going to be concerned with only the constraints that are going to be tight in our linear program. The tight constraints defined where this corner point is. That is, these are the tight constraints that are active at our particular basic feasible solution. So any constraint that's not tight, we cross out that row of the matrix and get rid of the corresponding entry in our right-hand side vector B. What we're left with is a new matrix that we're going to call ABC. This matrix ABC is going to be a square matrix. Recall that the number of elements in our basis is equal to the number of tight constraints. It's also going to induce a new vector, or a new feasible solution, xb. xb now is the basic feasible solution associated with our basis, but it's only the positive entries of that solution. There's no zero entries inside of xb sub b. We also have a new vector, a new right-hand side vector, b sub c. This is the right-hand side vector that remains after getting rid of all of the loose constraints, all the constraints that aren't tight. We can be a little bit more clear about exactly what these indices are. The index b corresponds to the basis that we're considering. The index c is corresponding to the tight constraints. With this reduced system, we can understand a few of the properties. First, the matrix ABC is totally unimodular. ABC is a submatrix of a matrix that was originally totally unimodular, so it itself is also totally unimodular. Also, ABC is square. The size of the basis is the number of tight constraints, so this is a square matrix. Because it's a square matrix, and because we have a non-degenerate solution, the inverse of this matrix exists. This is because XB is feasible and non-degenerate. Finally, because A is a totally unimodular matrix, or rather ABC is, this inverse doesn't just exist, but it's also an integral matrix. This follows because ABC is a totally unimodular matrix. With these properties in hand, we can start talking about which of these entries are going to be integer. We know that our matrix inverse is going to be an integer matrix. And also our original vector b is going to be an integer vector. So this side of our equality is going to be all integers. It's an integer matrix times an integer vector, which has to result in integers. As a result, the remaining entries of our basic feasible solution, xbb, has to be integer. Since this is all the positive values of our original basic feasible solution, and all these positive values are integer, when we add the zeros back in, we retain all integer values. So our basic feasible solution associated with this basis has to be an integer solution. Throughout this proof, we made one small assumption that our original basic feasible solution was non-degenerate. This isn't very important, and in fact we can prove the same thing for degenerate solutions as well. The point here is that if we have a linear program with a totally unimodular constraint matrix and an integer vector b, that any basic feasible solution is going to be integer.